Good morning. So today we study about the one of the responsible factor which control the incoming solar radiation on Earth. That is the astronomical control that we previously learned a little bit in our previous class. That is the change in Earth's uh, position during its rotation around Sun, and due to that, the incoming solar radiation can vary. So, Earth's climatic condition also affected due to that. So that we discuss in detail in today's class. Now, as we know that Sun is the ultimate arbiter of Earth's climate, because we know that most of the external energy which is responsible for governing the climatic conditions on Earth atmosphere, that is coming from the radiation energy radiated from the sun. So small amount of abnormality in this insolation energy can cause a change in the climatic condition of Earth, and this change can happen in thousands of years, or in even hundreds of years, or even millions of years. So with different change in the insolation energy coming from sun due to the astronomical changes may cause different scale of climatic changes. That means those climatic changes can be repeated, can have a cycle from minimum hundreds of years ranging up to few millions of years. The episodic nature of Earth's climatic change have been caused primarily by the cyclical changes in the Earth's circumnavigation of the eccentricity and precession are the three dominant cycles, or you can say these are the three dominant factors which are responsible for the difference in insolation energy, and these three are first uh, calculated, or they are first described by an Serbian astronomer and mathematician named as Milutin Milankovic. So from his name, these three cycles together, they are also known as Milankovic cycle, and the effect for these three factors, or for these three cycles on Earth's climate condition, is also known as Milankovitch orbital effects. Now, if we look at the Earth's present day orbit around the Sun, we know that Earth's orbit around the Sun in an elliptical path, and this elliptical path is basically a result due to some complex interaction. Basically, it's a complex gravitational field between different bodies: gravitational field of sun, gravitational field of different planets in the solar system, uh, as well as gravitational field of other celestial bodies within our solar system. They act together, and due to which the Earth's orbital path around the sun becomes a ellipse, or elliptical in shape. Now, the elliptical orbital path of the present day Earth's condition, uh, that path is not a constant throughout the history. This elliptical orbital path of Earth vary with time, and that variation occurs at cycles from 20,000 years to 4 lakh years. Now, due to the variation of Earth's orbital path, there are some changes found to occur on Earth. What are the changes? That is the shape of the Earth's yearly path of revolution around the Sun. That is, sometimes the orbital path of Earth becomes more elliptical, and after some time it becomes more circular in nature. Second, tilt of Earth axis. We all know that Earth axis at present day tilted around uh, 23.5 degrees. Now this tilting of Earth axis is also not fixed. It also varies with time. So this variation can also affect the Earth's climatic condition. And the third one, that is the relative position of solstices and the equinoxes around the orbital path of the Earth. That is, during the movement of Earth around its own orbital path, the timing of occurrence of equinoxes. Equinoxes are those days in the year in which the length of the day and night are same, and solstices are those days in which there are two solstices basically. One is the summer solstices, in which the daytime is maximum compared to the night time, and in winter solstices the night time is maximum compared to daytime. And this definition of solstices is uh, for the northern hemisphere. For southern hemisphere, when there is summer solstices in northern hemisphere, then daytime is greater than night time, but in southern hemisphere night time is greater than daytime, so just opposite. So the relative position, as we know that the equinoxes occur in the present time during the month of March and September. So this timing of occurrence of equinoxes and solstices during the movement of Earth around Sun, the timing will also changes. Now, how they will change and how they will affect the Earth's climate, that we are going to discuss in the next few slides. So these are the three cycles which are responsible for Earth's climatic condition. First one is the eccentricity. As I already told you that during the orbital movement of Earth around Sun, the path, orbital path of Earth also change with time. Sometimes it become more circular, and sometimes it become more elliptical. Next is the obliquity, that is the inclination of Earth's own rotational axis. Third is the precession of equinoxes, that is the timing of occurrence of equinoxes also changed with time. Now these three cycles have a cyclicity of around 1 lakh years, that is the eccentricity cycle. Obliquity cycle is around 41,000 years, and the precession cycle has cyclicity around 23,000 years. So you can see that these three cycles are not match exactly with each other. They have different cyclicity in their own. So the first cycle is known as obliquity, the tilting of Earth's axis. So as we are concerned on Earth's climate, that is why we are uh, describing it as tilting of Earth's axis, but it may be tilting of any planet axis. That may be Mars, that may be Saturn, that may be Uranus, or any planet axis. So any planet whose axis is tilted with respect to the orbital plane, we call them as obliquity. Now in this picture you can see that tilting of all planets are shown, and you can see most of the planets are tilted with respect to its orbital plane to some degree, although that tilting amount varies among different planets. Now what is the result of obliquity? If there is no obliquity, there will be no seasons. So all the seasonal changes that we are observed in Earth, that is during some time of the year we feel hot condition, that is summer, and again after some time we feel winter cold condition. So these seasonal changes will not be there if Earth's axis was not tilted. So because of the tilting of Earth's axis, we face or we experience the seasonal changes. Now, how these seasonal changes occur, that I am coming to describe in the next slides. So, what is the reason for seasons? As I already told, that is the tilting or obliquity of Earth's axis, that is the axis around which Earth rotates itself is tilted to some extent. Now, how seasonal changes occur? You can see that here at the present day, Earth's axis is tilted around 23.5 degree, and this tilting can vary from 21.5 degree to 24.5 degree. So between 21.5 degree to 24.5 degree, the tilt of Earth axis can vary. Now, how we measure the tilting of Earth's axis? We measure the tilting, that is the position of equatorial plane with respect to Earth's orbital plane. This angle is the obliquity or tilt angle. Another way of measuring Earth's tilting is the if we draw a vertical line over the Earth's orbital plane, and now from that vertical line, if we measure the angle between the vertical line and the Earth's axis. So by two way we can determine the tilting. First way, the equatorial plane and the orbital plane, the angle between these two planes. In the second case, orbital plane over which we draw a vertical line and measure the angle between that vertical line and Earth axis. Now what happens due to the tilting for which seasonal variations occur? You can see when the Earth axis is tilted at this position, northern hemisphere receives maximum insolation energy because sun incoming solar radiation from sun that falls vertically over the 30-degree northern latitude, near about 30-degree uh, northern latitude, that is over the Tropic of Cancer, that is 23.5 degree. So at this latitudinal condition, incoming solar radiation fall vertically, and as we move away from this latitude, we can see that the incoming solar radiation fall at an angle and also spread over a larger area. Now, from our previous class, we came to know that those places, those points over which the sun ray falls directly or perpendicular, those receives maximum insolation energy, and as we move away from those points toward the higher latitudes, their insolation energy falls at an angle, and the same energy is distributed over a larger area, so less amount of insolation energy received. So at this position we face summer in northern hemisphere, and as the southern hemisphere receives less amount of energy, and you can see that southern pole almost did not receive any um, insolation energy. So in the southern hemisphere the people face winter season. At the same tilting position, when sun rotates around its orbital path and goes to this opposite direction in this side, here the sun's uh, here the earth's position would be like this, and you can see here at this side the southern hemisphere receives the direct, that is tropic of Capricorn receives the perpendicular or direct solar radiation. So Tropic of Capricorn now receives maximum insolation energy, whereas Northern Hemisphere receives minimum energy. And here at this time, Northern Pole almost did not receive any incoming solar radiation. So at this time, Southern Hemisphere, they will face summer, that means hot condition, whereas Northern Hemisphere, they will face winter. So throughout the movement of Earth around its own orbital path, due to this axial tilting, different places of two hemisphere of Earth, they will face different seasons during different times of the year. So you can see when Earth is in this position, then northern hemisphere people face summer and southern hemisphere people face winter. When Earth is in this position, there is the winter solstices in the month of December. Northern hemisphere people face winter and southern hemisphere people face summer. And these two positions, that is the time in March and September, in these days, the length of day and night are same. That is, the incoming solar radiation falls directly over the equator. But in other positions over the orbital path, incoming solar radiation either directly or perpendicularly falls at different latitudes in the northern hemisphere, or the incoming solar radiation falls directly or perpendicularly at different latitudes in the southern hemisphere. So accordingly, the seasons in northern and southern hemisphere varies due to the direct falling of incoming solar radiation in different positions of Earth around its own orbital path. Now, what happens if there is no obliquity? That is, Earth axial tilt is zero. The Earth axis occurs if at a 90-degree angle, that is perpendicular to the um, orbital plane. So what happens? Then sunlight will always fall directly or perpendicularly over the equatorial region, and as we move towards the higher latitudes from the equator, the insolation energy becomes lesser and lesser. So at this position, equatorial plane or equatorial region receives the maximum insolation energy. Similarly, at this position also, that is the opposite side of the orbital path, the maximum insolation energy falls or receives at the equatorial portion, at the equatorial region. And away from the equator towards higher latitude, insolation energy becomes gradually decreasing. So maximum as maximum insolation energy received at the equator, so the most hotter portion of the earth becomes the equatorial region, and away from the equator temperature gradually decreases. But what occurs throughout the year? You can see that throughout the year always the equatorial region is the portion where sunlight falls directly, sunlight falls perpendicularly, and that falling of sunlight is not varying throughout the year. So all the places of the earth, they will receive the same amount of insolation energy throughout the year. So there will be no variation of insolation. That is why there will be no seasonal variations. So if by somehow the earth's axis becomes vertical, then there will be no seasons. So it is the obliquity or axial tilting of earth which is responsible for the seasonal variations. So when obliquity is high, that means earth's axial tilting is high, summer in both hemispheres receive more radiative flux from the sun and winters less, and when obliquity is low, summers receives less insolation and winters more. So obliquity high means that the difference in receiving incoming solar radiation of a particular place, say for example this place, if obliquity is high, then the difference of receiving incoming solar radiation of this place in different positions around the orbital path of Earth is highly varies. But if the obliquity is low, that is the Earth's axial tilting is more close to the vertical nature, that is it becomes sorry, this becomes like that, then there will be less variation of receiving the incoming solar radiation. So thereby seasonal variations will be less. So more axial tilting, there will be more seasonal variation. Less axial tilting, less seasonal variation occurs. So increase in obliquity causes difference in radiation received, especially at higher latitudes. That is especially found to occur in the higher latitudes, and thereby accentuate seasonal differences. So simple changes in axial tilt, what we learned that if there is no tilting, then solar radiation will found to always occur perpendicularly over the equator. So no seasonal changes in solar radiation at different points of the earth throughout the entire year. All the points of the earth receive same amount of solar radiation. So thereby no solstices and equinoxes present, and there will be no seasonal variation. Now if axial tilting becomes extreme, that is if the earth's axis becomes tilted at an angle about 90 degree, that is earth axis becomes almost parallel with respect to the orbital plane, you can see this picture. So one hemisphere of the earth receives 6 month sunlight and the other hemisphere is in dark. In opposite side, the other hemisphere, say for example the southern hemisphere, in this condition received 6 month incoming solar radiation, and northern hemisphere receives no solar radiation, that is northern hemisphere is in complete darkness for 6 months. So The two hemisphere receive 6 month light and six, that is 6 month solar radiation and 6 month darkness. So that will cause extreme seasonality. So when northern hemisphere is in this condition, that is northern hemisphere receives all the incoming solar radiation, so there will be extremely hot for 6 months, and southern hemisphere did not receive any incoming solar radiation, so there will be extreme cold. At this condition, southern hemisphere receives extreme or all the incoming solar radiation, so southern hemisphere there will be extreme hot, and northern hemisphere is in complete darkness with no incoming solar radiation, that is extreme coldness. So if earth axis becomes horizontal, or it is 90-degree tilted, that is parallel with respect to um, the orbital plane, then there will be extreme seasonality. Now if we look at the degree, sorry, there is a mistake, that will be 21.5 degree. The earth's axis tilting varies between 21.5 degree to 24.5 degree, and this variation in axial tilting, that is the change in axial tilt from 21.5 degree to 24.5 degree, that cyclicity occurs in a period of 41,000 years. So you can see from this graph, in the x-axis, that is the axial tilting, and in the y-axis, that is the time, millions of years. Uh, so you can see that this is the extreme position, that is a 24.5 degree or highest tilting of earth, and from one highest tilting to another highest tilting, it will take around 41,000 years. So this is the 41,000 year cycle, or cyclicity of axial tilting. So as you can see that in this 41,000 years, Earth's obliquity is changing gradually. That means axial tilting changes gradually. So depending on that, the incoming solar radiation, the amount of incoming solar radiation also changes in this 41,000 year cycle. So this will either amplify, accentuate, or suppress the seasonal changes. So when the axial tilting is around 24.5 degree, there will be more seasonal variation, more extremity between the summer and winter, more differences between the temperature in summer and winter of a particular place. And when the earth axis tilting is around 21.5 degree, that is more uh, close to the um, vertical nature, and that condition, the less difference between the seasonal changes of summer, or seasonal variations in summer and winter time for a particular location, and these variations in temperature or variations in climatic conditions particularly well observed or well identified in higher latitudes. Next cycle, that is known as eccentricity. Eccentricity of Earth's orbit is a secondary factor for seasonal changes. We can see that um, for the seasonal changes, the main responsible factor is the Earth's axial tilting or obliquity. Now, eccentricity means how perfectly the Earth's orbit is close to a circle. We all know that Earth's orbit around the sun is a elliptical in shape, but this elliptical shape is not permanent. This shape basically is a result of different um, planets and sun and other celestial bodies over the earth. As a result of these different gravitational forces acting over earth, the earth's orbit was not a perfectly circular in shape, but rather it is an elliptical in shape, and this elliptical shape also changes with time. Now how we can see that the earth's orbit is not circular? If we look at the earth's position around sun at different places in its orbital path, we can see that there are two positions in which the distance between sun and earth either becomes extremely low or becomes extremely high. The position at which the distance between earth and sun is minimum, that is about uh, 14 lakh uh, 14 crore 73 lakh kilometers. That position, that is the closest position or nearest position between sun and earth, that position is known as perihelion. Whereas when the distance between sun and earth is maximum, that is about 15 crore kilometer, that is known as aphelion. So you can see there is a distinct difference between the distance from earth and sun at different positions around its orbital path. So that explains that the orbital path of earth around sun is elliptical in shape. It is not perfectly circular. And this elliptical orbital path of earth is also not fixed. It has also changed with time from nearly circular, that is close to a circle, to more elliptical or more eccentric. Now, how eccentricity is measured? If we look at the elliptical shape of any thing, we can see that there are two axes. One is the semi-major axis, that is the A, or you can say this is the long axis, and the other axis is the semi-minor axis, that is the B. Now, when the length of these two axes, when the length of semi-major axis and semi-minor axis are same, that is A is equal to B, then eccentricity becomes 0. That means our orbital path is perfectly circular. So this is the equation by which eccentricity values are determined. Now, as we already observed, or we already came to know, that Earth's position at different points around its own orbital path changes, and thereby the distance between Earth and Sun also varies. So sometimes it comes more closer to Sun, that position is perihelion, and sometimes it goes far away from Sun, that is the aphelion positions. Now this orbital path sometimes becomes more circular and sometimes become more elliptical. So the distance of perihelion and aphelion also changes with the change in the shape of orbital path. Now here you can see in this animation that if you look at the circle shape, then at for this circle there will be a center, that is the cross-cutting point of the semi-major axis and semi-minor axis. And in case for a circular shape, the two axes are always same in size or same in length. So the center is from the center, all the points of this circle have been occurring equal distance. But in case of an ellipse, there is no one center. Instead, there are two centroids, and as the Earth orbital path is an ellipse or elliptical in shape, and Sun is not occurring at the cross-cutting point of these uh, of the two axes, semi-major axis and semi-minor axis. Earth is never occur in this cross-cutting point. Earth always occur in the elliptical orbital path of the Earth at a centroid position. So as the eccentricity increases, the or centroid position or the position of the Sun also changes. Now, the difference between the perihelion and aphelion, that also changes with changing eccentricity. Now, in case of ellipse for this particular place, you can see when the eccentricity value, this case, is less than 0.3 degree or about 0.3, the eccentricity value is about 0.3, then it looks almost circular. We are not able to identify them as an elliptical body, but they are elliptical mathematically. And interestingly, all the planets of our solar system, they have a eccentricity value of less than 0.3. So although we are telling or we are continuously reading that Earth's orbital path is elliptical in shape and sometimes it becomes more circular to more elliptical, but it will never exceed the eccentricity value of 0.3. So always it is more close to circle or circular shape. So the eccentricity of Earth's orbit varies at two periods. One is the 1 lakh period, another is the 4 lakh 13,000 years time period. Now, if we look at the values of eccentricity, how it changes with time, we can see that in present day, the eccentricity of Earth's orbit is almost at its minimum, that is 0.0167. You can see that is less than 0.0 less than 0.3, so very close to uh, a circular shape. But at times it was found that the greatest eccentricity of Earth's orbit, it becomes or it became about 0.06. So when the eccentricity value becomes 0.06, the Earth's orbit is mostly elliptical. That is the maximum elliptical shape achieved by Earth's orbit. And when it becomes very close to zero, that means Earth's orbit is very close to a circular shape. Now you can see if we consider the present day position, the 0.0167 eccentricity value. So this is the present day Earth's eccentricity value. We can see that there are two cycles. Gradually, this eccentricity value increases and decreases in a first order cycle, in a lower order cycle. So you can see the from 0.01 values, it is if we go to past, we can see that the values starts increasing, then decreasing, again increasing, reach up to 0.04 value, then again start decreasing, then again increasing, reach up to 0.05 value. So this way, with a smaller cyclicity, with smaller ups and downs, the eccentricity value changes, and the distance or the time span between these two successive peaks is around 1 lakh years. But if you look, or if you draw a smooth curve around these minor undulations, you can see that will become like this. So you can see, although there are smaller undulations, but there is a broad curvature in which there are several peaks. This is one peak, this one is one peak, this one is one peak. So this is a higher order cycle, and this cycle is around 4,13,000 years time taken to be repeated. So that is why the eccentricity cyclicity has two periods. One is the 1 lakh years, another is the 4,13,000 years. Now, although eccentricity of Earth's orbit varies with time, but its effects are very small. The difference of change in incoming solar radiation at any point over the Earth, due to this change in eccentricity, the difference is about 0.2%. So very negligible amount of change in incoming solar radiation observed due to change in eccentricity, and this 0.2% change in insolation energy is almost equivalent to the radiative forcing of 0.45 omega per meter square. That is the assuming the present day albedo ratio, or present day albedo value. So for change in eccentricity, the change in incoming solar radiation is very negligible, so thereby it has very low or lesser control over the change in Earth's climatic condition. The next cycle is known as axial precession, or it is also known as Earth's axial precession. Axial precession is basically the obbling of Earth's own axis. So like a spinning top, Earth's axial or the position of Earth's axis, that also rotates in a circular fashion. You can see that if this is the present day Earth's axis position, this axis is also facing at different directions throughout time. So Earth's axial direction is also changing with time, and this is known as axial precession. So axial precession does not describe how tilted the earth axis is, but rather it describes the changes in the orientation of this tilt. So the tilting may be at any angle, that may be 21 degree, that may be 23.5 degree, anything, but the direction of tilting, that changes with them. So sometimes the tilting is in this direction, sometimes the tilting is in this direction. So at present direction, that is facing towards Polaris. So that is why we are called that our North Star facing the Polaris, but it will not fix that Earth's axis always face Polaris. It was found that at some times ago, Polaris was not the North Star. Vega was the North Star. So in this way, Earth's axial tilting direction also changes with time. Now, The axial precession caused by gravitational pull of sun and moon on the bulge in earth diameter, and that is at equator. So slow turning of earth's axis of rotation causes earth's rotational axis to point in different direction, that is the oblique, through time. One circular path, one circular rotation of earth's axis takes about 25,700 years, nearly. Now, not only Earth's axis is oblique, but there is another contributor, that is known as precession of ellipse. That is the entire elliptical orbital path of Earth that also slowly change its position. So if this is the present day orbital path of Earth, you can see that also changing its position slowly with time. You can see how they are changing. So you can see now the orbital path, elliptical path comes here. So from starting its journey from this position, now comes to this position. So this is known as precession of ellipse. So precession is basically two types. Here you can also see that's the shifting of elliptical orbital path and thereby shifting of perihelion and aphelion points. So previously the perihelion is here and aphelion is here. Now due to the changing position of orbital path, perihelion shifted to here and aphelion shifted to here. So there will be two types of precession. One is the axial precession, in which Earth's own axis changes positional direction and rotates in a circular path, that is known as axial precession. And the second type is the change in Earth's own elliptical orbital path's position, that is known as precession of ellipse. So together axial precession and precession of ellipse causes the precession of the equinoxes. That means the positions or occurrence or timing of equinoxes and solstices are also changing depending on these two changes. Now you can see the precession of the equinoxes at due to the Earth's oval and rotation of its elliptical orbit, that is the axial precession and precession of uh, elliptical path, how it changes. If we look at the present day condition, we know that at present day it is the March and September time in which the equinoxes occur, that is the length of the day and length of the night time are equal. And for northern hemisphere in June 21, that is the summer solstice, that is the time of daytime is maximum and night time is minimum, that is summer dominates. And during December it is the winter solstices, that is the daytime is minimum, summertime is sorry, night time is minimum. So winter season occurs during this time for northern hemisphere. Now the position of these timing of these equinoxes and solstices, they varies with time. You can see from the present day, if we go 5,750 years from now, we can see that the equinoxes timings are changes. After 5,750 years, equinoxes will occur at the time of June and at the time of December. And the summer solstice occur at September and winter solstice occur in March in northern hemisphere. Another 5750 years, the equinoxes occur in September and March, although it is occurring September and March, but you can see that positions are changing. And summer solstice occur in northern hemisphere during the month of December, winter solstice during the month of June. Another 5750 year, that is the 16,725 years, that is the uh, position of equinoxes, that is equinox occur in December and another equinox in June, summer solstices in March, winter solstices in September, and after another 5750 years this position comes back. So in every 23,000 year cycle, the timing of occurrence of those equinoxes and solstices, they are changing, and this cycle is known as precession of equinoxes. So it is basically a simplification of complex angular motions in three-dimensional space, and this precession of equinoxes is basically a result of two precessions. One is the axial precession and the other is the precession of Earth's elliptical path. Now, change in insolation by precession. If the precession of solstice and equinoxes are uh, not there, that means it is around a perfectly circular orbital path and there is no change in axial precession or no change in um, orbit of Earth, so there will be no change in insolation. And as this condition is not actually occurring, so what we are facing, that is the change in eccentricity, that means change in eccentric orbit of Earth with time, and the change in the direction of axial tilting, that is the axial precession. So depending on these two changes, the precession of equinoxes and solstices occur, and that will affect a change in insolation energy at different times of the year. So depending on that, the relative positions, that means the timing of occurrence of solstices and equinoxes changes, as I showed you in this previous figure, that the occurrence of equinoxes in which in the present day occurs in the month of March and September, that will change in a 5750 years about um, 90-degree position, about 3 months accentuate. Similarly, change in aphelion and perihelion and precessional change in axial tilt will also occur. So these are the relative change in positions occurs, and due to which the insolation uh, change also found to occur over the Earth's surface due to precession of equinoxes. So in summary, we can say that the gradual change in Earth's orbit around the Sun result in changes in solar radiation, and there is no human interference for this change in incoming solar radiation. We cannot control anyway the amount of solar radiation that Earth receives. It is naturally occurring starting from the origin of the solar system. So gradually, with time, these cycles repeated again and again with those um, cyclicity. cyclicity. So that will evidence different incoming solar radiation at different seasons, and also it varies in different hemisphere. And these factors or astronomical factors, they have different cyclicity. Earth's axial tilt has a cycle of 41,000 years. The precession cycle is about 23,000 years. Eccentricity varies in two cycles. One is 1 lakh years, another is 4 lakh 13,000 years. And together with certain amount of variations in this cyclicity, if we modulate them with time, they then this cyclicity together becomes more and more complex. You can see that orbital scale changes in climatic records. So this is the 1 lakh year cycle, how it changes. This is the 41,000 years cycle, and this is the 23,000 years cycle. Now, if we combine the cycles together, the effect of these different cycles shows a varying combination. And if we combine all the cycles together, it becomes sometimes impossible to identify from their different cycle. They have a look on the combinations. This is the 1 lakh year cycle and the 23,000 year cycles. If we add them together, it looks like this. This is the 41,000 year cycle and the 23,000 year cycle. If we add them together, it looks like this. And when all the three cycles, that is the 1 lakh year cycle, 41,000 year cycle, 23,000 year cycle, these three cycles are combined together, you can see it looks more complex. So from this graph, it is almost become impossible to identify individual cycles. And apart from that, there is another cycle, that is the 4 lakh 13,000 year cycles. So with this, the modulation of the amplitude, that is the variation in the degrees of the different cycles, also happens through time. So if we combine this with this cycle, it becomes more and more complex. So without very precision study, without very careful study, it becomes almost impossible, because what we get the record in the rock record or in nature, that is the product by combining all these cycles together. In nature, they will not told us that this is the 1 lakh year cycle, this is the 23,000 year cycle. What we found is the combination of all these cyclicity and ultimately the product. So from that product, we have to distinguish, we have to make these kinds of complex uh, cards, complex cyclic cards, and we have to study them very carefully and try to identify the different cycles from those cards. So now if we summarize the whole thing, so this together, the Milankovitch effects can change summer insolation, arriving at the top of the atmosphere at around 65-degree latitude in the northern hemisphere, particularly by around plus minus 12%. So depending on these Milankovitch effects, all those cycles, the incoming solar radiation can vary in higher latitudes around 65-degree north by about 12%. The 23,000 year precession cycle has been the dominant cycle in solar irradiance at lower and middle latitudes during the summer, that is more close uh, important, or it has more effect near the equatorial region, whereas the 41,000 year obliquity cycle is the dominant Milankovitch effect, for which seasonal changes are observed, and that is particularly well observed in higher latitudes. The 1 lakh year eccentric cycle is the weakest among all the cycles, all the three forcing factors. So that's all about the Milankovitch cycle or Milankovitch effects, or you can say the astronomical control of solar radiation. But keep in mind, these are the natural cycle, and any biotic body, or particularly the human, does not have any control over this cyclicity. This is occurring naturally, and this will go on until the solar system exists. Thank you.